So now we're going to get into some more details in the principles of security in operating systems. There is a term that is pretty hot nowadays. It's called secure by design. And that means that an operating system or an application or hardware has embedded security from the beginning. So we're reviewing here the principles that maintain security in the design of operating systems. The first principle is the keep it simple, silly principle, where the simpler the design, the easier it is to test, verify, so verifiably secure operating systems. And of course, the easier it is to embed and also change things and expand operations. Now, that is a little difficult with an operating system, as you can imagine. However, it is a good principle to keep in mind when one designs or adds features to an operating system. Now, the second principle is about layered design, which we reviewed from the beginning of this chapter. We looked at ring structures or different levels or that the operating system loads, hardware, kernel, operating system, and user. And that layered design, again, helps with the separation of concerns, but it also helps with debugging issues and isolating problems. Now, trust is a big word over here, and the layered trust that is being discussed here, we discussed again in the beginning of the chapter when we were talking about the rings of trust, and the inner ring is the most trusted, and the outer, the least trusted, that has the user applications and all that. And it also assists with what we call encapsulating specific functionality to specific rings of trust, and then depending on the level of trust, assigning different responsibilities. The kernelized design is something we did not discuss about. So as you probably have understood, the kernel is integral part of the operating system. It's its heart, its core, and it executes the lowest functions such as synchronization and inter-process communication. So adding security to the kernel in a separate module, which we call secure kernel, is a very good way to enforce security in a modular way and assure that we have complete coverage of security, because through the kernel, all the operations go through. Also, it's important to have a separate security kernel and not just embed security to the kernel. So that's the separation of concerns. That is a good thing. In addition, the unity of operation, one part of the kernel only does security, is a good thing that is accomplished with the security kernel. And of course, modifiability, it's easy to modify because it's only responsible for security. Compactness, it's small. This security kernel is a small, and because it's small, it's easier to verify its operation. Another secure principle in the design of an operating system is the reference monitor, which we discussed also when we were discussing access controls. And the reference monitor is part of the security kernel, and it controls the access of different objects. Now, again, part of the security principles, which I mentioned before also in the kernelized design, is correctness and completeness. And that's something that many times in my research I've tried to prove in order to prove that my design is secure. So correctness means that we know what we are doing, and we're doing it properly. Like, let's say we're trying to protect from denial of service attacks, and we're doing it correctly, and we're actually protecting from denial of service attacks. Coverage is, completeness is about coverage. It's about checking whether we have wide coverage and we are fulfilling the scope of security that as promised. Correctness can be proven with formal reviews or experimentation or simulation, and coverage, of course, can be shown with experiments and other such metrics for security. Now, the secure design principles that are used for the security of an operating systems refer to the principles of least privilege, which we discussed before in access controls, economy of mechanism, open design, complete mediation, permission-based operations, separation of privileges, least common mechanisms, and ease of use. All of these concepts that we reviewed as we were discussing about this chapter and the security for operating systems. Finally, one big concept is the trusted systems. And I will expand a little bit on the trusted systems function. So trust is very difficult to define, and trusting trust is kind of tough. Trusted systems are systems that you can actually prove that they're doing their job properly, fairly, they are working, operating correctly, and they have ways to enforce integrity, limited privilege, and things like that. Proving trust is very difficult. There's a whole diatribes written about trust and how we define it. And truly, many times I personally say I don't trust anything, any code that I haven't read, but at some point you have to have some trust, or else you will have to invent everything from zero on your own. So, so these are the principles that we've reviewed, or we will be reviewing some of those in the next slides, and they're very good principles for operating system security, but also for general system security, application security, and so on and so forth. Now in here, we're getting a little deeper into trusted computing base. And this is defined as everything necessary for a system to enforce security policies, and it may be split into functions that may be a subset of the operating system. Hardware can be as low as the registers and buses, communication buses, and all that. But it can also include processes. So if these are trusted processes, like security critical processes, primitive files that access the security in a database, or protected memory, and of course inter-process communication. The trusted computing base that was defined quite early in the computing history, in the 70s and 80s, also includes, besides functions, the design, the relevant code that runs in a protected state, and of course implementation that in operating systems, for example, the implementation of security is the security kernel. This trusted computing base was established early on, and it was within the effort of standardizing security and having some ways and some abstractions to define trust and trusted systems. So in this slide, the security kernel shows all of these trusted computing based principles in one. So hardware, operating system modularization, and things like that. So the security kernel is a very important part of an operating system. It may have multiple lines of code, thousands of lines of code, and it has it is designed based on security. It interfaces with the hardware, it monitors operating system accesses to hardware, and performs all the needed protection functions. Other system functions that need to be trusted, of course, startup, because that is a tricky one, where malicious code could be started up with normal application code. Also, trusted path is a system function that precludes interference between operating system and user. That's what was accomplished with the fence and other memory protection, the newer memory protection mechanisms such as paging. Um, and object reuse, that's a function that we need to look into and always sanitize and not leak any data that shouldn't be accessed in an unauthorized manner. Finally, audit that we discussed earlier on in this lecture, in the previous video, which is logs. And even these logs could be tampered, so they need to be protected. And sometimes we may need to audit the audit logs. So with that being said, there are some very interesting books that I'm showing next. Unfortunately, I don't have this book with me, the orange book that talks about trusted system functions and is in the next slide. So the Orange Book is a part of the historic series of the Rainbow series that you can look up, and you can even find these in an archive online. These are very historic books about security that were created by the Department of Defense, and the NSA was not named NSA at the time. They're very pioneering for their time. I personally have the vintage hard copy version, so I usually show that in my class. Currently, I have this in my office, so you're not going to get to see it, and also browse through it as I usually do in class. It's a really interesting series, the Rainbow series. Like I said, very novel, things that the Department of Defense was looking at back then, 30 years ago, sometimes as researchers are discovering right now. So the DoD was worried about information assurance, and that's why it put all of this work to define trusted systems. There were 6 rankings, and in each ranking for each step, the security was increased. This Orange Book is historic for what it defined at a very early time. As you can see, this is 1985. It created common criteria for a trusted computing base, which would be separation of functions, assurance, and features that are selected independently. This has become a multinational standard, and this common criteria is not about limiting functionality, it's about allowing multiple users at a time, and it's very very novel for its time and very looking forward, looking ahead. It was also very open-ended, and this way, and that is one of the reasons why it's still very valid, and we reference to it. Of course, computer systems have changed tremendously since 1985. However, still the principles for security and trusted systems are valid. So the last topic that we will review, which is very interesting, is about malware for operating systems, and a specific kind of malware called rootkit. Rootkit takes its name from root, which, as you know, is God in the operating system. The root user has privileges to do anything, install, uninstall things, create users, give privileges to users, take privileges away from users. In a few words, I mean, and back in the day when I was growing up and I was an undergrad, we called the root the God of the operating system. So the rootkit's goal is what the adversary's ultimate goal is, to give a user the ultimate root privilege. So you may have stolen a password, for example, from a user, but this doesn't do you much good for them campus systems, because you're not root. And you may have noticed in our campus specifically, simple users cannot even install anything on computers. So what's the point? So the rootkit is a tool, or a set of tools that obtains these privileges. It's quite mainstream, actually. If you Google the word, you will find free rootkit being given. It's a kind of standard tool for script kiddies that they download and they try to use to get root privileges. Now, the actual hackers actually write, new exploits to create rootkits. So the interesting thing at the time of mobile phones is that there's rootkits for your phone. And these rootkits are very interesting because they can turn on your microphone, send text messages, and violate your privacy by giving away your location, respond to queries, drain the battery by turning on your Bluetooth, and other great things. The thing with these phone rootkits is that they're easily downloadable, especially in markets that are not very well checked or very moderated, such as the Android Play Store. And do not get me wrong, I'm not against the open markets and all that. I actually like the Play Store better than the Apple Store because as a developer, I can easily put my app over there, but the user has more responsibility in that case to secure their phone and not download from unknown, untrusted parties. So nowadays, of course, Google is doing a lot to secure the market and the phones by doing scans, like malware scans, to find this kind of rootkits, but they're pretty detrimental. They're pretty detrimental because they can be undetectable by the user, they can work in the background, and because the operating system of a phone, it's the minimum operating system compared to a PC, although the complexity is increasing as our phones are becoming more and more like computers. It is fairly easy to make rootkits and more difficult to detect. Of course, the rootkits for PCs were the first ones that came to circulation, and their goal is also to evade detection. Your book refers to an example that has to do with Windows, but it could apply to Linux operating system as well, where there's a sequence of API calls, for example, in an application. As you can see, that it inspects all the files, and a rootkit may intercept the sequence and inject itself and make itself to be executed. And this is a very nice way of going undetected. So as we check files, the rootkit may put itself in between the files that need to be executed and get executed and get root privileges to the adversary that is using this. It is fairly easy for an antivirus to miss these rootkits that are working on a stealth mode because they may become part of the operating system kernel. So the worst thing is to download one of those, and that can be done via phishing campaigns.